Good day, students. Welcome to part 5 of the integration review series. In this clip, we're going to be going over the trapezoidal rule. Okay, so to get started, let's go ahead and take a look at what the rule is, where it came from, and then we're going to apply it to an example. Okay, so let's say we have a function with the following curve, and what we want to do here basically is we want to estimate the area under the curve. Okay, so let's say there goes our coordinate system. This is the y-axis, and there's the x-axis. And let's say we have a curve that looks like this. Curves up, and then down, curves a little bit, and it goes like that. All right. All right, so let's partition it by threes, just as I did right here. And let's say this curve right here, this is a function f of x. And what we're trying to do is we want to estimate the area under the curve from A all the way to B. Okay? And our tool for approximation that we're going to be using today is the trapezoidal rule. Okay? So let's say that the lower bound of your interval is x sub 0, and then the next one is x1, x2, x3, and let's say this pattern continues all the way to x of n. So let's say the upper bound of your interval is x of n, and then this has to be x of n minus 1, and this is x of n minus 2, on and on like that. All right? So what would the trapezoid look like? So what we're going to do is, you see every input value we have here, we're going to trace it to the curve. So this point right here, this point right here is f of x sub 0. You can write it down. So this is f of x sub 0. It's basically this length. And then we trace this point. This is f of x sub 1, f of x sub 2, f of x sub 3. And we'll just follow that pattern going on all the way to f of x sub n. Okay? So there are different ways we can do this. We went over the midpoint and LRAM in previous videos. You can go over those if you haven't already done so. So what does a trapezoid rule look like? Well, what we're going to be doing is we're just going to be using these points to draw a trapezoid. Okay? So starting from here, there goes my first trapezoid, like that. Okay? There's the first one. And then the second one, like that. And then the third one, just like that. And then we just basically follow that pattern to draw our trapezoids in all the areas between the curve and the y-axis. Okay, so there goes the next one. And you notice that all my trapezoids have a base of 3. I spaced them with equal bases, okay? And I did that for a reason, because that ties into a formula, okay? And then there goes our last trapezoid. Okay, so what we're going to be calculating today is basically the area under each trapezoid. So this area right here, under each trapezoid, that's an estimation of the area under the curve. Okay? All right, so let's go ahead and write down the formula for the trapezoid rule and talk about why it makes sense. Okay? So this is a trapezoid rule. Trapezoid rule. Trapezoidal. I keep calling trapezoid. Trapezoidal rule. Um, Basically, if you wanted to estimate the area on the curve, which is basically the integral from a to b of f of x dx, it's going to be approximately the t sub n, which is trapezoid rule using n subintervals of equal length, equals h over 2 times y sub 0 plus 2y sub 1 plus 2y sub 2 plus dot 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 plus 2y sub n minus 1 plus y sub n. Okay? Another, we also have to note when the interval AB is partitioned into n subintervals, of equal length. Okay, equal length, and let's call that length h, as indicated in our formula right here, which would be b minus a over n. Okay, so that's what h is. So in this rectangle, in this scenario I drew here, all these lengths right here, they're h. Okay, basically the height of the trapezoid. Okay, so that's all h. So what this formula basically tells you is the area under each of these trapezoid, the sum of all the areas. All right. Another variation that you might see in some textbooks is exactly the same as this, just some additional substitutions have been made. That is another variation. Uh, the area from a to b of f of x dx is approximately the trapezoidal rule using n sub intervals of the function f of x is equal to b minus a over 2n times f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 plus dot 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 plus 2f of x sub n minus 1 plus f of x sub n. Okay? These two formulas are exactly the same thing. Y sub 0 is the same thing as f of x sub 0, and then f of x sub 1 is the same thing as y sub 1. Well, the further process they did here was they substituted b minus a over n, this is an n right here, into this h right here, so we have b minus a over 2n. So any of these formulations will work. In today's example, I'm going to be making use of the first one, okay? Any of them will suffice, so there you have it. Okay, so where did this formula come from? Well, I'm going to show you the logic, reasoning behind it right now. If you don't care about where it came from, you can always skip forward to the example and see the application of this formula. But let me just show you the background of where this formula came from, okay? So think about the area of a trapezoid. Area of a trapezoid. What is the formula for the area of a trapezoid? Well, let's sketch it first, okay? So let's say we have a trapezoid of this nature. Smaller. And the formula is basically the following. If you have h as a base, and then as a height, sorry, and then b1 and b2 are the parallel sides, the area is basically 1/2 of b1 plus b2 multiplied by h. Okay, so that's the area of a trapezoid. And the way I remember it is I tell myself half sum of parallel sides times the height. Okay, that's the area of a trapezoid. So this is just one trapezoid. If you look at the case of the trapezoidal rule, we have multiple trapezoids. They are all adjacent to each other, sharing a common side length. Okay, so what does that look like? What are the consequences of that kind of configuration on the resulting area formula? So let's say we have multiple trapezoids. Okay, let's say we have 4 trapezoids. Let's see, so this is the first one. Let's say the first one looks something like this. I'm going to make them all have equal height, okay? We have the first one like this, and then the next one is like that. And then the next trapezoid goes like that. And then the last trapezoid, oh, I just messed up. I need to make it have equal base, so that was a little bit too long. So say it goes like that, right down. And then the last trapezoid looks something like this. Okay, so we have 4 trapezoids here. So the question is, what is the area of this figure, all these trapezoids in simplest form? Okay, you see that when we derive that expression, you see where the trapezoidal rule came from. Okay, so in this case, we have this side length right here is b1. This is b2. This is b3. This is b4. and this is B5, okay? And then this length right here is H, they're all uniform length by design, H, 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 okay? So what is the expression for A1 plus A2? I'll use a different color so it doesn't look messy. What is the expression for A1 plus A2 plus A3 plus A4, okay? What is the area going to be? So let's write the combined area. It's going to be the expression. The first A1 is 1/2 B1 plus B2 times H. That's for this rectangle. And then add on A2. A2 is going to be 1/2 times B2 and B3 are the parallel sides for A2. So 1/2 B2 plus B3 times H. All right. And then move this over to the side. And now we're going to shift to A3. The third area is bounded by B3 and B4. So it's going to be plus 1/2 B3 plus B4 times H. And then A4 is going to be 1/2 of B4 and B5. B4 plus B5 times H. Okay? All right, let's simplify this. You notice that every expression has H and a 1/2, right? So we could factor that out, right? So we have 1/2 H can be factored out as H over 2 times B1 plus B2 plus B2 plus B3 plus B3 plus B4 plus B4 plus B5. Okay? You notice something happening here? You have a repetition of all the interior side lengths, right? They're all repeated. So if we simplify further, we have H over 2 times B1 plus 2B2 plus 2B3 plus 2B4 plus B5. Okay? So you see the similarity between this and the trapezoidal rule. All right, so what do you want? The key takeaway here is you have to double all the interior lengths because they apply to two trapezoids, okay? But the beginning and the last lengths you do not double. All right. So let me show you the trapezoidal rule we came up with before. You see how the interior lengths are doubled, but the exterior lengths y sub 0 and y sub n are not doubled. All right. So that's the main idea for how the trapezoidal rule came about. Okay. Now another cool fact that is good to note is that the trapezoidal rule with n sub intervals is equal to the left endpoint rectangular approximation using n equal sub intervals plus the right endpoint rectangular approximation using n sub intervals divided by 2. Okay, divided by 2. All right, so let me quickly show you the derivation of this result. Again, you don't have to view this. It's just FYI. You can always skip ahead if you don't care about this result. All right. So let's see. How is this the case? Well, let's do just a short review on rectangular approximation. What I'll do is I'm going to start with a line. Let's say we have a segment. Okay. So we have a segment like this, and they're spaced evenly and into n equal sub intervals. All right. Starting from it, we have x sub a, which equals x sub 0, 1, 2, 3, x sub 1, 1, 2, 3, all the way down to x sub n, okay? And x sub n is equal to b, all right? And this is x sub n minus 1. All right, so what is the left endpoint rectangular approximation going to be? When you're doing the left endpoint rectangular approximation, you are going to be making rectangles using the left, starting with the left endpoint. So you're going to start with this all the way to here, okay? You do not pick the last point. The rightmost point gets neglected, okay? So that's going to become the height. Each one has an equal height of h times times y sub 0 plus y sub 1 plus plus y sub n minus 1. Okay? If I distribute this h to everything, you're going to get area equals base times length times height. um, well, length times height, yeah, or length times width for each expression. Okay, so h times y sub 0 is the first rectangle and on and on. All right, so that goes LRAM with n subintervals. Now, what is RRAM going to look like? What is RRAM? RRAM is similar, but in that case, for RRAM, we're going to start from x sub 1 all the way to the rightmost endpoint, neglecting the leftmost endpoint, okay? All right, so what is that going to look like? That's going to be h times y sub 1 plus y sub 2 plus da 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 plus y sub n minus 1 plus y sub n. Okay? So there goes the right endpoint rectangle approximation. All right, so what if I want to compute the left endpoint rectangular approximation using n sub intervals plus the right endpoint rectangular approximation using n sub intervals divided by 2. What would this be? Well, let's see. So since I'm dividing by 2 is the same thing as multiplying by 1/2, right? So I'm going to multiply 1/2 by the sum of these two expressions. So I'm going to have 1/2 multiplied by h times y sub 0 plus y sub 1 plus dot 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 plus y sub n minus 1. This is the RRAM. I mean LRAM, sorry. This is LRAM, okay? And then I'm going to add on RRAM because we're adding LRAM and RRAM. So RRAM is going to be h times y sub 1 plus dot 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 plus y sub n minus 1 plus y sub n. Okay? So there you have it. All right, so if I add these two expressions together, what happens? Well, you notice that I'm multiplying this quantity and this quantity both by h, so I can factor that h out. So if I factor out the h, I'm going to have h over 2. And then notice what happens when I add. This y sub 0 has no common term to be combined with, so it stays y sub 0. If I add the y sub 1s, I'll have 2y sub 1. And then if there are y sub 2 there, they'll repeat in both cases. So I'll have 2y sub 2 plus da 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 da. Y sub n minus 1, they both repeat, so you also have 2y sub n minus 1. And notice the rightmost point length, height, is y sub n, because it's by itself. And what do we have? This is the trapezoidal rule using n subintervals. Okay, so it's kind of cool to see that when we average the left rectangular approximation and the right endpoint rectangular approximation, we average them, we get the trapezoidal rule, which is pretty cool. Okay, now that we've gone over some derivation, let's take a look at an example, okay, using the trapezoidal rule. So example number 1. Example 1. This is a question. Use the trapezoidal rule with n equals 4 to estimate this definite integral, which is an integral from 1 to 3 of x squared dx. Okay? Alright, so to compute this, first thing I need to find is h. Alright? So what is h? H is basically, remember, it's b minus a over 2. In this case, our intervals, I didn't say the interval, we're going from, well, you can tell what the interval is. How do you tell what an interval is? You look at the limits of integration, right? So this is the a and that's the b. So our interval is basically 1 to 3, which equals a to b. Okay? So a is 1 and b is 3. Okay? So let's plug that in here. So we're going to have 3 minus 1 over 2. So 3 minus 1 over 2 is as follows. Wait a minute, just quick correction. Formula for h is b minus a over n. So let's fix that. So h is v minus a over n, and n is 4. So it's 3 minus 1 over 4. So 3 minus 1 is 2 over 4. 2 over 4 is 1/2. Okay, so that's h. Sorry about that. All right, so now what does that tell me? Well, let's draw a line so that I can know exactly what my input values are going to be. So we are starting from 1 all the way to 3, okay? So let's say this is 1, 1 to 3, 2. All right, let's make it 4 points. So 1, 2, 3, 4, 2, and then 1, 2, 3, 4, 3. Okay, we have two intervals, but we need n equals 4. So how do we make this 4 equals of intervals? We have to split it down the center, right? So I'm going to split it down the center right here. This is going to be 1.5 or 3 over 2, and this is going to be 2.5 or 5 over 2. So we're starting from this point. This is going to be my x of 0. This will be my x of 1. This will be my x2. This will be my x3. And this right here will be my x4. Okay? So those are the values I'm going to be plugging into my function. All right? We need 4 intervals, and they are all of length what? They're all of length 1/2. All have equal lengths of 1/2. Okay? So this is the setup that I need to give me a visual as to what I'm going to plug in into my function. All right? So let's set it up. The antiderivative from 1 to 3 of x squared dx is approximately, in this case we're doing t sub 4, and that is equal to h over 2 is you know what, let me write down the formula first so that we don't get confused. Okay, so t sub n, let's just write down the formulas so you all can understand exactly what's going on. So this is the exact problem. So t sub 4 is a problem. Let me put the formula up here. Let's shift this down a little bit, and then I'll put the formula above it so we can have a visual as to what is going on. All right, so this is a formula again. I don't want to be scrolling up and down, so I'm going to just put it here. So the integral from a to b of f of x dx is approximately t sub n, which equals h over 2 times y sub 0 plus 2y sub 1 plus dot 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 plus 2y sub n minus 1 plus y sub n. Okay? Alright, so let's apply that here. Now note, h is 1/2. We're going to do 1/2 over 2. Be careful here. This is where people make most mistakes, okay? 1/2 divided by 2 times y sub 0 is the output when you plug in the x sub 0, okay? So y sub 0 is going to be f of, I'm going to put a lot of intermediate steps here so no one gets confused, okay? So it's going to be f of 1. You don't have to do this if you understand this formula. So it's going to be f of 1 plus, I'm going to double the next one, which is 3 over 2, double 3 over 2. Everything in the interior gets doubled. So this one gets doubled, this gets doubled, this gets doubled, that one doesn't get doubled. Okay, per the formula, the first and the last lengths do not get doubled. Okay, so I double f of 3 over 2, and then the next one, y sub 2, you plug in x sub 2 plus 2 f of what? 2, right? And then the next one is 5 over 2. You double that as an interior input, f of 5 over 2, plus the last one is 3, f of 3. You do not double that, okay? So there you have it. All right, so what is f of x? F of x is x squared, so I'm going to be putting in all this input values into the function x squared, and then I'm going to be calculating what it is, all right? So what is 1/2 over 2? We can put this over 1. And then if I multiply this by the reciprocal of that, I'll have 1 over 4, okay? Because this flips up to 2 over 1. We can just multiply this by 2 over 1, and then this by 2 over 1. And then you end up with 1 over 4, okay? All right, times, remember I'm showing you all the intermediate steps so that we do not get confused, okay? F of 1 is going to be 1 squared plus 2, f of 3 over 2 is going to be 3 over 2 squared Okay, plus 2, f of 2, you're going to plug into the function, which is going to be 2 squared, plus 2 times f5 over 2 is going to be 5 over 2 squared, plus f of 3, you do not double that, right? So just 3 squared. Okay, now it's not arithmetic, right? So let's use order of operations to simplify this. We're going to do the parentheses first. All right, 1 squared is just 1 plus 3 squared over 2 squared is 9 over 4. So it's 2 times 9 over 4 plus 2 times 2 squared is 4 plus 2 times square that is 25 over 4 plus 3 squared is 9. Okay? Alright, let's simplify it a little bit further. We're going to have 1 over 4 times 1 plus, if you reduce this, 2 goes here, 1, 2 goes here, 2 plus 9 over 2 plus 8 plus, you reduce this, 2 goes here, 1, 2 goes here, 2, so you have 25 over 2 plus 9. Alright, put all of them over 1. You can find the LCD. The LCD of 1 and 2 is clearly 2, so times this by 2, by 2, times it by 2, by 2, times it by 2, and times it by 2. Okay? If you add it all up, you're going to have 1 over 4 times 70 over 2, which equals 1 over 4 times 35. Okay? Alright, so if you multiply this out, this is going to be 35 over 4, which is equal to, you can write this as 8 3/4 or 8.75. Okay, so this is your trapezoidal approximation using for subintervals. Okay, so there you have it. So thanks so much for taking the time to watch this video. Please feel free to subscribe by clicking up here. You can help support by liking this video or posting a comment. More videos can be found on mathworkshop.com. Thanks again and have a wonderful day.